Quick review of lifting agents. We talked about frontal lift, orographic lift, convergence lifting from low pressure, and convection on a hot day. So let's look at those in greater detail. Along an advancing cold front, especially, or associated with an occluded front, are common areas where we're going to see frontal lifting, causing storms that are caused by this frontal activity. So cumulonimbus clouds. And here's just a good picture of, we have some cumulonimbus clouds that are forming along an advancing front. You can obviously see them and they're pretty well organized in a line. This is likely due to some sort of frontal lifting action that is occurring. The next kind of lifting action we can see is orographic lift, again, caused by mountains. So if you might live in a mountainous area, if you visited a mountainous area, we have some air that is getting pushed aloft, we have moisture in the air, we have instability, and we have a lifting action, and that is that orographic lift. That air gets forced aloft, and we can see in the background of this picture here, we can see, looks like some thunderstorms have formed in the distance here, and you can kind of see them. I think there's another one that's forming up here, maybe some anvil cloud tops over here that we can expect to see some thunderstorms from this type of lifting called orographic lift. The next kind of thunderstorm, which is probably the most common, I would call it a garden variety thunderstorm, is an air mass storm. So here's an example of one. We have just a large amount of rising air, and we get these generally from convective type activity when they just start heating and cooling the Earth's surface at different rates. It's just simple convection. If it's not associated with a front or frontal activity, we're going to call this an air mass thunderstorm. It's very common in East Texas where I live. We get a lot of this activity happening in the afternoons in the summer with a good amount of heating of the Earth's surface. It's just simple convective activity. If it's not associated with a front, we call it an air mass storm. And here's just a radar view of an area just to the south of me that has a lot of different air mass activity of thunderstorms that are popping up. It's not associated with a front. We can see there's no front involved here. If we looked at the larger view of the weather picture, these are just ordinary air mass thunderstorms. Here's a view of the weather picture and the area here on the radar. If you look at this area down here and you're not familiar with Texas geography, we're basically looking at this area here of Texas. So it's basically here and we don't have any frontal activity going on. Quick review, what kind of front do we have up here crossing Oklahoma? If you said that's a stationary front, you would be correct. Good. Okay. So this is just an air mass thunderstorm. We have just ordinary convection happening here. Then we have a lifting action we called convergence, okay? Again, low pressure, sucking in moisture, all of it just jams up, kind of like leaves floating into the middle of a swimming pool, whirlpool. It just gets jammed up, can't go anywhere, all kinds of debris and junk. Well, that air gets lifted. If we have moist air coming in, it gets jammed up, gets lifted up. If we look for areas of moisture, here are some areas, and if I am taking a look at this chart, now we haven't looked yet, let me zoom in, haven't looked yet at surface analysis, or we haven't looked at METAR observations or any of that, so don't worry too much about the numbers here at this point yet. But if I take a look at these numbers, and let me just demonstrate on one of my station models, I'm going to circle the temperature and I'm going to circle the dew point, and then we'll zoom back in and talk about it. So I've circled the temperature on the top right there. It's 72 degrees Fahrenheit. These are shown in Fahrenheit on this chart. The bottom number, 69 degrees Fahrenheit, that's our dew point. So we see that it's only 3 degrees apart. If we look just to the west of the station that I've circled on here, you see GVT. The temperature there, 73, the dew point, 72. Okay, the temperature and dew point are very close together over at GVT. So, and also at OSA, we have plenty of moisture, okay? So if we look for those temperature dew point spreads that are close together, that means, if you think back to our discussion of humidity, and when the temperature and dew point are the same, then we have 100% saturation of the air. These areas mean if we have close temperature and dew points, we have more moisture going on. So areas that I would expect moisture here are areas where the temperature and dew point are close together. So that is our second ingredient. We talked about lifting action. Second ingredient is moisture. The third ingredient for thunderstorms is stability. So stability, let's talk about this. So we have talked about stability when we covered clouds. So if you want to go back and review those videos, that might be helpful if you're confused. But we want to talk about stability in terms of a couple different ways. The conditionally stable and unstable. So what's the difference between conditionally stable and unstable? Well, we say that unstable means that our lapse rate is greater than basically going down at 3 degrees Celsius per 1,000 feet. So if the lapse rate is going down at a rate that is greater than 3 degrees per 1,000 feet, then we would call that an unstable atmosphere. A conditionally stable atmosphere is going to be one where the lapse rate is going down at between 1.6 degrees Celsius to 3 degrees Celsius, again, per 1,000 feet. So with that lapse rate going down at 1.6 degrees Celsius to 3 degrees Celsius per 1,000 feet, so somewhere in there, we call that a conditionally stable lapse rate. So here I've got what's called a skew-T chart. We've kind of seen these before when we talked about upper air observations with radio sonde balloons. Let me zoom into this. And, all right. So if we look here, we have a couple lines going on here. We have a red line that shows our temperature. We have a blue line that shows our dew point. So let's look at that red line. If we look at the red line and we follow that line upward on this chart, we can see that it actually does not change very much with altitude. In fact, we're going up to, just with looking at this chart, I'm going up to about like 500 millibars, and we're not really seeing hardly any change in the temperature. So this is basically saying this red line is nearly vertical, saying below like 10,000 feet, it's nearly vertical. And that means that it's not changing very much at all with altitude. So this is not going to be very unstable, because if you recall our discussion about stability when we talked about it with regards to cloud development, if we have the surrounding air around a parcel of air that goes down in temperature very fast, then a warmer air parcel has the energy to continue rising, because it's like that hot air balloon that's full of hot air. Surrounding air is cooler, that warm parcel of air has energy to keep rising. So if we have an unstable lapse rate, that means that the surrounding air is going to cool off very fast, faster than 3 degrees per 1,000 feet. So that would be a condition of instability that we would expect to see thunderstorm development. It could still happen with 1.6 degrees Celsius to 3 degrees Celsius per 1,000 feet, but that's conditionally stable, and that is going to be possible development of thunderstorms, but it just kind of depends on what that air that's in that balloon or that bubble of air that's rising, what its temperature is as well. And we're going to talk about the life cycle of the thunderstorm on our next video.